Hello. Now we will study the polarization. So polarization we will study for dielectric material. So let's first study what are dielectric material. So we all know there are multiple types of solids. We categorize them into two categories, two broad categories, conductors and the insulators. Conductors are the materials in which there are lot of free electrons are there. So since there are a lot of free electrons are there, they are easily through these conductors the electricity pass through. So if I'm having a conductor and if I give the charge, some charge to the conductor, that charge will dissipate throughout the material. We don't have any control over to it. And this charge will dissipate through the conductor till there is a non-zero electric field inside the conductor. Okay. And then we have the insulators. In case of insulators, if I'm having an insulator and if I provide the charge to the insulator and let's say onto this side, the charge will remain there. It is not going to move. Okay. So here there are a lot of electrons are there, free electrons are there. The moment you provide the charge, then because of the existence of non-zero electric field inside the material, these electrons starts moving and they move till the electric field is there. But in case of insulators, if there is a non-zero electric field is there, but since there is no free electron inside, there is only atoms and there is only valence electrons. These valence electrons cannot move outside of the atom because there is a lot of attractive force applied by the nucleus to these electrons. So these electrons cannot move away, move out. This electric field is not that sufficient, which will be sufficient to move these electrons outside. Okay, so the electric field remain there non-zero. So this is a conductor, this is a insulator. Insulator does not oppose the external electric field, but the moment in the conductor there is an external electric field is there, the electrons will move till the electric field is there. Then comes the dielectrics. These dielectric materials are basically insulators. So in case of dielectric, there is no free electron. So these are in total insulators. So to define the dielectric, what we are going to do, we are going to categorize the insulators into two categories. Two categories based upon the existence of dipole moment. So we all know each material made up of atoms. And we have multiple types of atoms. An atom consists of a positive charge and a negative charge. Negative charge in terms of electron, and that is valence electron, and positive charge in terms of nucleus. So there are some atoms, examples, hydrogen, oxygen, nitrogen, or you can say, the multiple atoms are there. In these atoms, if you see, not the nitrogen one. So in these atoms, you see there is a positive charge and the negative charge, basically, they coincide. The center of positive charge and the center of negative charge, they coincide at a single point. And because the center of positive and negative charge are coinciding at the same point, their own dielectric moment is zero. So they don't behave as a dielectric because the positive charge and the negative charge, they lie onto a same point. But similarly, at the same time, there are atoms which are not conductors like HCl, and you can have this HCl is there, 2SO4 is there, multiple atoms are there. So in these atoms, if you see, there is a positive charge and there is this negative charge. For an example, if you see the HCl, this HCl is made up of two particles. There is this H plus and there is this Cl minus. So this H plus will be having a net positive charge and the Cl minus will be having net negative charge, and there will be a distance between these charged particles. And since there is a distance, so these particles, if you talk about, these particles, they have non-zero dielectric moment. And we already know when non-zero dipole moment. So we already know when we talk about the dipoles have their own electric field. So if I'll be talking about the HCl, each and every atom of HCl will be having its own non-zero electric field. So if I construct a material, let's say if I construct a material made up of HCl. So if I'm having a material this time, system is there, and this material is constructed of the HCl particles. So since this is made up of HCl, this is made up of particles, and these particles obviously will be randomly arranged because ultimately we are talking about the material. So there will be this plus, minus, plus here, minus here, minus here, plus here, minus, and that's how it will go on. So all these atoms, all these molecules, basically HCl molecules, they will be having their own electric field, and that electric field will be non-zero. So if any point, let's say I'm calling that point as P, if at any point you want to calculate the net electric field due to this whole substance, that net electric field will be the vector summation of all the electric fields created by the individual molecules. And since in this case, all these molecules are randomly arranged, since all these molecules are randomly arranged, on the basis of that we can say each and every electric field, the net of each and every electric field finally will become zero because they are randomly arranged. Or randomly arranged, or you can say they are not arranged at all. So we are having multiple molecules which individually generates the electric field, but combinedly their net effect is zero at point P. Okay. So at point P, they are not generating any electric field because the electric field generated by each and every molecule is being cancelled out, and that is being cancelled out because they are randomly arranged. If somehow I can arrange them in the sense basically, if I can start tilting them somehow, if I start tilting them, so if I start tilting them, I'll not be changing their individual electric field because I'm not changing the distance between them, I'm not changing the charge over to the molecules. What I'm doing right now, I'm tilting them. If I tilt them, then there is a possibility that at a point P, when you will calculate the net field now, after tilting all these molecules, the net field might be non-zero. And that's what happened with the dielectric materials. So dielectric materials consist of these kind of molecules. Dielectric materials consist of the dipoles. These consist of the molecules which acts as a dipole, which are not neutral. Though charge-wise they are neutral, but they generate their own electric field. Each and every molecule generate their own electric field, but that electric field we are not able to see because of the random structure of the molecules inside the material. If somehow we can tilt them, if somehow we can arrange those molecules, we will be able to see the net electric field due to these molecules in combined or the substance in totality. So that's what we do in this chapter. Polarization, in case of polarization, what we do, we tilt them. With the external use of electric field, with the use of external electric field, this external electric field will be applying a torque onto each and every molecule, and that torque will tilt the molecules. The tilting will happen because of this external electric field, and because of that tilting, this particle P, this point P, will observe the electric field outside one and the field generated by the net effect of this dielectric. So what happened? This is the unorganized structure. When we organized this system with the use of external electric field, you found that each and every molecule gets rearranged. This is a hypothetical case scenario I'm making. I'm making them parallel. In reality, they don't become parallel. Okay, so I'm making it a parallel. So what happened? Each and every molecule will rearrange itself so that the electric fields this time will not be zero. Hypothetically, I made them parallel. Since I'm making them parallel, then the field due to each and every molecule, each and every dipole, this time will add. It will not cancel out each other, this time will add. And that will give us the net electric field inside points. Okay, and now you see, since electric field I'm taking in this direction, so electric field is from the positive charge particle to the negative charge particle. Okay, so because of this electric field, since electric field is in this direction, so positive charge particle, since electric field is from the positive to negative, so positive charge particle will experience the force in the direction of electric field. So in the direction of electric field, these positive charge particle will move away, and this negative charge particle will get attracted towards the direction of electric field or opposite to the direction of electric field. So this whole structure, if you want, you can define this whole structure as the negative charge comes to the one end and the positive charge comes to the other end. Basically, we want to solve the equation, and we want to solve the equation using this conductor analysis. So in case of conductor, charge particle moves, but in case of dielectrics, charge particle don't move. This is, in reality, there is a tilting which happens in case of molecule, and because of the tilting, we cannot calculate the electric field because we don't know. We are talking about the atomic labels. So tilting we cannot calculate. So hypothetically, what we did, we made them parallel. But again, by making them parallel, we cannot calculate how many dipoles are there, because the net electric field, because of this whole system, will depend upon the number of dipoles, which will depend upon the number of molecules. Okay. So what we do, this whole system, this whole structure, hypothetically we equate this whole system with a conductor, because ultimately this whole structure is going to create its own electric field. The same thing conductor do. In case of conductor also, the redistribution of charge creates the own electric field of the conductor, and that electric field opposes the external electric field. Okay. So similarly here also, this redistribution of dipoles I'm defining as the redistribution of charge. So I'm assuming that effect of this structure or effect of this structure is similar to this structure. In this structure, I'm assuming the negative charge particles are moving on one end and the positive charge particles are moving on other end. And this redistribution of charge within this material will create its own electric field. I'll call that electric field as induced electric field. Induced, why? Because if this external field would not have been there, the tilting of the molecule would not have happened. And if this would not have happened, electric field will not be generated because of the system. That's why I'm calling it as an induced. And as you can see, this induced electric field is opposite to the direction of external electric field. In case of conductors, the induced electric field used to be opposite, but as well as same in magnitude. And that was the reason, in case of conductor, the net electric field inside the conductor was always zero. But in this case, since it's not actual conductor, I'm converting the dipole, this dielectric, into a conductor. Okay. So in this case, E induced will not be equals to the external, but it will be opposite to that. So if you want to calculate the net electric field inside the material, that net electric field will be the vector summation of external plus induced. And if you talk about this induced electric field, the direction of induced electric field will always be opposite to the external one. So E induced will be anti-parallel to E external. And this E induced obviously will be less than E external. And I'm using the sign equality or equality sign also, because if this dielectric converts into the conductor, this will become equal. Okay. So that's how the dielectric works. In case of dielectric is nothing but an insulator. It is insulator. There is no free charge. There are no free electrons inside the dielectric. Okay. The insulators we divide into two categories. The insulator which are inside the insulator, in which the molecules are not having any dipole moment. So they are not having any dipole moment, they are perfect insulators. There will be no effect of any external electric field onto that till we breach a level. Actually, if we go for very, very high value of electric field, in that case, even these materials will become dielectric, or after some time it will become conductor. That we will study later on. But there are materials, insulators, which have non-zero dipole moment. The individual molecules in the insulator have non-zero dipole moment. So in case of these insulators, these insulators in a combined, they don't show any electric field for us. Reason being, the molecule inside the material, they are randomly arranged. Since they are randomly arranged, the each and every electric field generated by each and every molecule gets cancelled out. But somehow, if I can rearrange the system, we know if I can rearrange the system, we can rearrange the system or tilt the system, we will be able to see the non-zero electric field due to this insulator. Okay, and that's what we do when we pass an external electric field through the system, because if you remember, in case of dipole moment, we have studied a formula that was tau is equals to P cross E. So whenever a dipole is placed on an external electric field, the dipole experiences a torque. So similarly, if I generate an external electric field, this external electric field will apply a torque on each and every molecule or dipole. And because of this torque, each and every dipole will have a tendency to rotate. The amount of rotation or amount of angular displacement will be different, actually, and we don't want to calculate that. Just to understand this concept, what we did, we made them parallel. So when they become parallel, we realize since the negative charge will be going opposite to the external electric field and the positive will be going in the same direction, so in this system, the induced electric field, when it will come, it will be opposite to the external electric field. Again, in this case also, we cannot solve the question, we cannot make the formulas. So what we did to make the formulas, this whole system, we converted this whole system with a conductor. And we assumed, let's say, this dielectric is having some free electron, though it don't have any free electron. So if it will be having some free electron, not the infinite one, free electron, if those free electrons are there, then these free electron will go on one end and the positive charge particle will go on to the other end. So this whole material will act as a large dipole. And this large dipole will be having its own electric field. And that electric field we call as a induced electric field. Induced because it is being induced by the external one. If you switch off the external field, this will go on. You will not be able to observe this one. Okay? So this is the thing. So we assume this system into this system. And the charges which gets redistributed here, we will call those charges as Q-induced. Induced charges. We will say that if we will be having a dielectric, if we place a dielectric in an external electric field, from now onwards, we will say that due to this external electric field, the negative charge will get induced on one side and the positive charge gets induced on the other side. This will be the minus of Q induced and this will be the plus of Q induced. And obviously the magnitude wise these two charges will be same because in the beginning this system was neutral. In reality there are no induced charges. In reality there are dipoles. And you see the electric field due to the tilting of dipole, not the movement of dipole, because the net force onto the dipole because of external field is zero. So dipoles don't move, molecules don't move, they tilt. Because of the tilt, they generate the non-zero field. And to study that non-zero field, we convert that system, actual system, into this hypothetical system. And the field generated by this system will be same as the field generated by this system. Because in this system, it's easy to make the formulas. So we make a hypothetical concept of induced charges. So there will be induced charges coming onto the surface because of the external electric field in case of dielectric materials. What are dielectric materials? They are insulators. But some special type of insulators. The insulators made up of molecules which are having non-zero dipole movement. They don't have free electrons, but they have the dipole which can generate the electric field. Okay? I think you understood this. Next lecture we'll be making the formulas. Thank you.